What we are talking about today is problems associated with complex power and such. So let's take a look at the following circuit. We have a 120 angle 0 degrees volt RMS voltage source connected to an impedance that I'm going to call ZA, which I will define shortly. We have an impedance here, ZB, which I will define momentarily, and an impedance here to the right, which I will call ZC. And on the right-hand side of the circuit, we have a 5 angle 45 degrees amps RMS current source. And let's say that ZA is equal to 10 plus J8 ohms. ZB is equal to 12 minus J3 ohms. And ZC is equal to 8 angle 30 degrees ohms. So there are a multitude of different things that I could ask about on this relatively simple circuit, right? I could ask you for the complex power absorbed or supplied by impedance ZA, ZB, ZC, or either of the sources. I could ask you at what power factor either of the sources operate at, as supplying power or absorbing power. So let's kind of do a mix of things here. Let's determine the complex power. Actually, I take that back. Let's determine the reactive power absorbed by impedance B. So we're going to solve for QB. Let's determine the apparent power absorbed by element C. So it's going to be the magnitude of SC. And let's determine the power factor at which the voltage source operates in supplying power. So PF, voltage source supply. All right, so those are going to be our three quantities of interest, more or less chosen at random just to illustrate things. All right. So in order to determine the reactive power absorbed by impedance ZB, we need to know either the RMS phasor voltage over ZB or the RMS phasor current flowing through ZB, or both of those quantities. I would argue only getting one of them is probably the easier move here. So I'm going to define those quantities. So I'm going to call this RMS phasor voltage VB. So this is one possible thing that we could be looking for. Here is RMS phasor current IB. Which of these two quantities would be easier to determine? DB, okay. I tend to agree with that because I look at this circuit and say, I could effectively apply Kirchhoff's current law at my top node and find VB with a single equation. So I tend to agree with that. IB could be done using superposition pretty easily. A source transformation on the left-hand side could be used in another way to calculate IB in 1 to 2 steps, but I think solving for VB directly by applying KCL is probably the easiest way to get one of those two quantities. So we'll take Connor's suggestion and use that approach. So what I'm doing is I'm simply applying Kirchhoff's current law to this node. And so what that will result in, let me do it in not red so it's not quite as abrasive on the eyes. I will have VB minus 120 angle 0 degrees volts RMS divided by my impedance ZA. So that's 10 plus J8 ohms plus my unknown voltage VB divided by my impedance ZB. So that's 12 minus J3 ohms minus 5 angle 45 degrees amps RMS is equal to 0. So we have a single equation and a single unknown, but to my knowledge, the numerical solvers that we have on our calculators don't really play well with complex numbers. So in order to actually get a numerical solution here, we're going to have to do a little bit of algebra, okay? So the first thing that I'm going to do is I'm going to move all of my constant terms to the right-hand side and all of my VB terms to the left-hand side. And so what that's going to look like is VB multiplied by a factor of 1 over 10 plus J8 ohms plus 1 over 12 minus J3 ohms is equal to 120 angle 0 degrees volts RMS over 10 plus J8 ohms plus 5 angle 45 degrees amps RMS. Now, the constant terms on the right-hand side can be expressed as a single complex number, and the coefficient of VB on the left-hand side can be expressed also as a single complex number. So I can say that this bit over here on the right, 120 angle 0 over 10 plus J8 plus 5 angle 45 looks like 11.097 angle negative 12.057 degrees amps RMS. And I'm just going to make a mental note here that I'm storing this in my calculator as X. I'm going to call this coefficient here, so that's 1 over 10 plus 8i plus 1 over 12 minus 3i. So that looks like 0.142 angle negative 11.819 degrees ohms to the minus 1 power. and I'm going to call it Y. And then from this, VB is equal to 11.097 angle negative 12.057 degrees amps over 0.142 angle negative 11.819 degrees per ohm, or simply X over Y in my calculator. And I get VB to be 77.917 angle negative 0.238 degrees volts RMS. Anyone was following along in my math, did they get a similar number? All right, so we have determined VB. How do we use this to get QB, which is what we're actually looking for? Okay. Well, the complex power absorbed by element B, by definition, is the voltage drop across B multiplied by the complex conjugate of the current flowing through B. We're not going to actually bother determining this current because we determine those alternative relationships at the end of last class, right? So we can express this purely in terms of our voltage. And so what this is going to look like is the magnitude of VB squared divided by VB conjugate. So that would be 77.917 volts RMS quantity squared divided by 12 plus J3 ohms. And so if you give me just a moment, I'm going to throw this into my calculator. I get 490.813 angle negative 14.036 degrees volt amperes, which I can express as 476.158 minus J 119.040 volt amperes. Which of these four numbers is the actual thing we're looking for? The negative 119.040. Absolutely correct. So from this, QB, which is the imaginary part of SB, is negative 119.040 bars. So at literally no point did we have to bother with remembering any trig identities or anything like that, or actually even an exact equation to calculate Q, right? We were able to determine the reactive power absorbed by this element, knowing only the voltage drop across it. That's the beauty of those alternative relationships that we developed at the end of the class on Wednesday. It lets us get our answers without having to do a bunch of extra computations determining quantities that really don't wind up mattering, okay? So we figured out what QB is. What's the other things that we're looking for? SC. So that is the apparent power absorbed by impedance ZC. Anybody have a thought on how we might go about that? Rajan, I think you raised your hand. Yes, sir. The magnitude of S represents apparent power. So S by itself is the complex power. That is exactly correct. So, excuse me, what Noah suggested is that we know the current that's flowing into impedance ZC already, so we don't even have to do any work at all if we use the alternative relationship for when the current is known. You're 100% correct. The apparent power is just the magnitude of the complex power. So we can say that SC, using our alternative relationships derived in class on last Wednesday, is the magnitude of the current IC times the impedance ZC. Okay. Well, the magnitude of our current is simply 5 amps RMS, and ZC was simply 8 angle 30 degrees ohms. And so this is going to give us a complex power of 200 angle 30 degrees volt amperes. Noah already told us what the answer is, but I'm going to be sneaky and ask other people. So if I express this in rectangular form, it's 173.205 plus J100 volt amperes. Which of these four numbers is what I'm actually looking for? Pardon? Say it, yeah. The 200, exactly right. So the magnitude of the complex power, this portion right here, tells us that the magnitude of SC is 200 volt amperes. Exactly what we were looking for, and exactly what Noah suggested like 3 minutes ago. Yes, sir. The apparent power is what the electric company produces. The average power is what they bill for or what we pay for. Average power is what's used by the consumer. So we pay for what we use. So average power is what the consumer pays for. Apparent power is what the utility produces. Rajan. So 173.205 right here represents the real part of the complex power, which is the average power. The apparent power is the magnitude of the polar form. So that's exactly the reason why I'm expressing both representations, a polar form representation up here and a rectangular form representation down here. I'm trying to illustrate to you guys that if you can just do this simple calculation of finding the complex power S, you inherently know apparent power, average power, reactive power, and power factor angle, just depending on what type of answer you tell your calculator to give you. You don't need to do any more work for those quantities whatsoever. So being able to calculate complex power gives you everything else. So that's why I harp on calculating complex power and then figuring out, as opposed to memorizing a bunch of different equations to calculate any of these quantities directly. In my opinion, it's a waste of time and brain space. All right, so the last quantity that we're interested in is, I guess I should technically write that down since we did do a little something here. I'm calling, sorry, put the head of the arrow the other direction. This was the current IC that we use, which by inspection is simply the 5 angle 45 degrees being provided by the source. All right, so our last quantity that we're interested in here is the power factor at which the voltage source is supplying power. Okay. So to me, that means we need one single piece of information. What we need is the phase angle of the current that's flowing into the negative polarity terminal of the voltage source. Pretty hard to find the phase angle directly, so we'll likely just wind up finding the current and then get our phase angle from that. So let's put that in purple. So I'm going to call this IVS, and I've specifically defined IVS to be leaving the positive polarity terminal because I'm trying to calculate supplied power, right? So how might I go about determining that value based on the information that we already have? We could do KCL at that middle node. That will also work. Yeah. So we could say, we could use Ohm's law. Let's walk through the different things because you've actually suggested two different things, both of which will absolutely work, okay? So if we apply Kirchhoff's current law at this top middle node that I have a red dot on, which we did earlier, that's what our equation down here is. This first term, VB minus 120 angle 0 over 10 plus J8, represents negative IVS. So we could simply substitute in VB and determine it, right? Because we would be saying IVS is equal to VB over ZB minus 5 angle 45 degrees. So that's KCL at that top middle node. Or, and that would require us to know what the voltage VB is, which we do. Or we could simply use Ohm's law, which was the second suggestion Noah had, where we could say simply that 120 minus VB over ZA is equal to IVS. Both of those methods literally wind up doing the exact same thing because they really represent two different ways of looking at the problem, right? So I'm going to use the Ohm's law representation here real quick. So I'm saying that the current that's leaving the positive polarity terminal of our voltage source, IVS, is equal to 120 angle 0 degrees, volts RMS, minus VB. I'm gonna have to scroll up and find that real quick. 77.917. Angle negative 0.238 degrees. Volts RMS, all divided by ZA, which would be given by 10 plus J8. And so if I throw that in my calculator, give me just a moment to do that if you don't mind. I get 3.286 angle negative 38.219 degrees amps RMS. Now, technically speaking here, we have all of the information that we need in order to calculate our power factor, but I'm going to go one step further for those of you who are kind of lazy and don't like remembering things here, okay? So I'm going to calculate the complex power supplied by our voltage source. So that is going to be SVS supplied, which is going to be the voltage drop across our voltage source, 120 angle 0 degrees volts RMS, times the complex conjugate of IVS. So that's going to be 120 angle 0 degrees, excuse me, I forgot my units, volts RMS times 3.286 angle positive 38.219 degrees amps RMS, because the complex conjugate operation changes the sign on the imaginary part of a complex number, which is exactly the same as changing the sign on the angle of a complex number. If I multiply these two things together, I get 394.356 angle negative 38.219 degrees, excuse me, volt amperes. Which is the same as 309.825 minus J 243.977 volt amperes. Okay. So now, yes, did I screw something up? You know what? I think I did this. I used the variable here instead of the variable conjugated. So I bet you're correct. So let's put a plus sign here and a plus sign here to fix that. So that was a mistake on my part. I saved this current as variable y in my calculator. And when I threw it into this equation, I forgot to tell the calculator to do the conjugate of y. I just did y by itself. So thank you for pointing that out. All right, so 3 different ways to calculate the power factor buried in this hullabaloo, right? The first way is literally the cosine of theta v minus theta I, which would simply be the cosine of positive 38.219 degrees. The second way is the cosine of theta s, which is the cosine of 38.219 degrees. The third way is to take the ratio of the average power, 309.825, over the apparent power, 394.356. And so cosine of 38.219 gives me 0.786. 309.825 over 394.356 gives me 0.786. Obviously, they should all give you the same number because it's the same thing. My preference is this middle relationship. And the reason why I prefer the middle relationship, even though they all give us the exact same thing, is because I can see definitively from the sine of this angle without doing any extra work whatsoever, whether or not my power factor is leading or lagging. In this case, my angle is positive, so my power factor is lagging. I have to do work to get a positive sign here, and I have no way to determine whether or not I have a positive sign using this relationship. So the middle method is the one I greatly prefer, which, not coincidentally, comes about from calculating the complex power absorbed or supplied by my element of interest. So I am fundamentally going to harass you to no end until you submit and agree that calculating the complex power is the right first move for any complex power related quantity. I will browbeat you into submission. All right, so how did we feel about that particular example? Hopefully nothing too wacky or wild. Oh, no problem. All right, so let's take a look at another way that I would like to represent circuits for complex power analysis. Okay. So let's say that we have the following circuit. Where we have an unknown source voltage, Vs, and this source voltage Vs is connected to some transmission lines, which have a characteristic impedance of 0.1 ohms plus J 0.2 ohms. And this transmission line is used to connect our source to 3 single phase loads connected in parallel. So here's load 1. Here is load 2. And finally out here is load 3. I like to call this style of problem an industrial problem because it's dealing with quantities that we could measure out in the field in order to perform these calculations, okay? So let's say that load 1 is operating such that it absorbs 30 kilowatts of power at a power factor of 0.8 leading. Actually, I'm going to change that to lagging, and I'm going to lump this into a new example problem in a minute. Let's say that load number 2 is absorbing 20 kilovolt amperes at a power factor of 0.9 lagging. And let's say that load number 3 absorbs 10 kilowatts at a power factor of 0.8 leading. And we are able to measure the voltage drop across our composite load, which I'm going to call VL, and find that it is 480 angle 0 degrees volts. Our goal here is to determine the power factor at which our source is supplying power to this system. PF VS applied. So we have a single goal, and we've been provided a lot of information, but this circuit doesn't look much like circuits we're used to analyzing. We absolutely have the tools to do this, but we need to think our way through things, okay? So what I mean by that is I would argue that the complex power that's being supplied by our unknown voltage source, Vs, is the same as the complex power that's being absorbed by our 3 composite loads, as well as any power that might be absorbed by our transmission line. Effectively, power in equals power out. Has to be true. Okay. So how might we go about solving for the complex power absorbed by, let's start with load 1. Okay. So I'm going to call this S load 1. Anybody have any thoughts here?
Getting the voltage in that.
Well, we know the voltage drop over it already. Okay. But we don't know what the impedance of it is. So that is absolutely correct. So Noah has suggested that based on the units we're told here, kilowatts, we know that the load is absorbing 30 kilowatts of average power. Okay, that's 100% correct, and that is integral to what we're going to be doing here. So we don't spend too much time on me harassing you guys about relationships that we learned literally 2 days ago. Recall the power factor is defined to be the ratio of average power to apparent power, which is the same thing as the cosine of our power factor angle, right? So if we know average power and we know power factor, we can solve for apparent power and power factor angle, which completely defines the complex power absorbed by load 1, right? So this is going to be the average power absorbed by load 1 divided by the power factor at which load 1 operates with a phase angle of the inverse cosine of the power factor at which load 1 operates. All of that is from manipulation of the definition of what power factor represents. Okay. Pardon? So yeah, we're going to wind up getting units of kVA out of this. Okay. So if we plug in our numbers here, our average power is 30 kilowatts. We divide by 0.8, and then we have an angle of inverse cosine 0.8. And so this is going to look like 30 over 0.8 angle inverse cosine 0.8. I get 37.5 angle 36.870 degrees kilovolt amperes. I'm just going to leave this in polar form representation because we don't really need to do anything with it, right? We're just trying to find the complex power, so it really doesn't matter which representation we have. Okay. So that's the complex power absorbed by load 1. For load number 2, we can follow a very similar approach, but there is one distinct difference here. Since you're told that this load is absorbing 20 kVA, someone other than Noah, tell me what these units represent. Does it have a phase angle?
Oh, it does. Apparent power?
Yes, so this represents the apparent power. Okay. So we already have this part of the complex power. We just need to find theta S now. Theta S will again be the inverse cosine of the power factor at which load 2 is operating. Okay.
So what are
So let's talk about that because we didn't introduce the phase angle in the previous thing, but I'm happy to talk about it because it is very important. So whenever theta S is positive, we have a lagging power factor. And whenever theta S is negative, we have a leading power factor. So what this lagging or leading in the description tells us is whether or not to put a plus sign or a minus sign in front of our inverse cosine function. Because the inverse cosine function is only going to return a positive angle. So whenever it's lagging, effectively we leave it alone. Whenever our power factor is leading, we need to include a negative sign to force the angle to be negative. because negative signs correspond for our angle correspond to leading power factors. So leading means theta I is leading theta V. Yes. So in this case, we are going to have 20 kVA with an angle of inverse cosine 0.9 which looks like 20 angle 25.842 degrees kilovolt amperes. So we've got S load 1, we've got S load 2. Let's calculate complex power absorbed by load 3. So what pieces of information were we given for load 3? 10 kilowatts represents average power. So we know P, we have the power factor, and we know that it's leading. So it's going to look extremely similar to our calculation that we did for load 1, except that we're going to need to include a negative sign in front of our inverse cosine function. So this is going to look like P3 over PF3 angle negative inverse cosine of PF3. Or 10 kilowatts divided by 0.8 with an angle of negative inverse cosine of 0.8. That should be, I think, 12.5 angle negative 36.87, but I'm going to put it in my calculator just to make sure. Yep. 12.5 angle negative 36.870 degrees kilovolt amperes. All right, so we have determined the complex powers that are associated with our loads. All right, so if we look back at our representation here, we know the complex power absorbed by load 1, 2, and 3. We do not know the complex power absorbed by our transmission lines, represented by that impedance 0.1 plus J 0.2 ohms. So to determine the complex power absorbed by our transmission line, we're going to need to know one of two pieces of information: the voltage drop across our transmission line or the current flowing through our transmission line. I would argue that the voltage drop across our transmission line is presently impossible to determine. And I say that because we don't know what our source voltage is, so we have no way to know what the voltage drop over it is. We do, however, have enough information to determine the current that's flowing through our transmission line. And what I mean by that specifically is whatever current is flowing through our transmission line winds up flowing through this composite load, right? It branches off and flows through those things. So we can calculate it in one of two different ways. We can use the fact that we know the complex power absorbed by each of these loads and the voltage drop over each of these loads to find the individual currents flowing through each branch and then apply KCL here. Or we can lump all these loads together into a single composite load that we know the voltage drop over and figure out the current that's flowing into this, the total current flowing into the node in one go. I am a much bigger fan of the second route because it's using information that we already know. Okay. So what I'm going to do is I'm going to calculate S total. All right, or S load total, I guess. S load total, which I'm going to say is simply S load 1 plus S load 2 plus S load 3 . So I have saved S load 1, S load 2, and S load 3 in my calculators as variables. So I'm just going to say X plus Y plus Z. And I get 66.662 angle 22.241 degrees. That degree sign looks too much like a 0 for my liking. Kilovolt amperes. How do I get my current from this? So if we know that S load total is equal to that voltage VL, because that voltage is the same voltage across all three loads, times the current IL conjugate. We can simply solve this for IL conjugate, right? So IL conjugate would be S load total divided by VL. Well, I want to get rid of this conjugate sign. So what I'm going to do is I'm going to take the conjugate of both sides. Because if I conjugate something, I'm changing the sign on the imaginary part. So if I conjugate something twice, I'm just going back to the original value. So from that, I can say that IL if my stylus will write, is going to be simply S load conjugate divided by VL conjugate. Because whenever I conjugate a fraction, I have to conjugate both the numerator and the denominator. You could do that too, absolutely. Either they're the same thing. I am going to say then that we have 66.662 angle negative 22.241 degrees kilovolt amperes divided by 480 angle negative 0 degrees. Yes. You're right. I misread my calculator. You're 100% right. I'm sorry. 62.662 is correct. No, that's all me. Just misreading the calculator and saw too many sixes in a row. Thank you for that. So I'm taking the conjugate of my power and then dividing it by 480. And I get 0.131 angle negative 22.241 0.241 degrees kiloamps RMS, which is the same as 130.546 angle negative 22.241 degrees amps RMS. Yes, sir.
So if our phase angle or voltage was 0 degrees, does that mean we're lagged by -22.4?
So the phase angle of the voltage is 0. The phase angle of the current is negative 22.241. So you are correct that the current is lagging the voltage through our composite load by 22.241 degrees. Yes. All right, so from here, calculating the complex power absorbed by our transmission line is fairly straightforward. It's very similar to what we did in our last problem. So I'm going to call this complex power S wire. Using our alternative relationship, it's going to be the magnitude of our current IL squared times the impedance of our wire, which is going to look like 130.546 amps RMS quantity squared times 0.1 plus J 0.2 ohms. Which I get to be 3,810.762 angle 63.435 degrees volt amperes, or 3.811 angle 63.435 degrees kilovolt amperes. I need to pay attention to the units here because I'm about to add this complex power absorbed by my wires to the complex power that's absorbed by my load. And if I don't do the units correctly, I'm going to get a wrong result. Okay. So my total complex power that is being supplied by my voltage source is the complex power that's being absorbed by my transmission line plus the complex power that's being absorbed by my composite load. So that's going to be 62.662 angle 22.241 degrees kilovolt amperes plus 3.811 angle 63.435 degrees kilovolt amperes. Making sure I remember what variables I use in my calculator. So T plus B. I get 65.577 or 578 actually, if I do rounding correctly. Angle 24.434 degrees. So, knowing this, how do I determine the power factor at which my voltage source operates? Cosine of this angle right here. Absolutely correct. So my power factor for my voltage source, PF VS, is simply the cosine of 24.434 degrees. Or 0.910 lagging. Where again, just I know I'm beating this to death. I know that this is a lagging power factor because the power factor angle is positive. Okay. So we've got 10 minutes left of class. I think that's enough time to expand on this little example problem slightly and do one more thing. And that thing is what value of capacitor C would we need to put in parallel with our voltage source to correct the power factor to PF new is equal to 0.95 lag. Okay. So that's our new goal. Take this system and then figure out how to properly power factor correct it. I am going to give us a necessary piece of information. I'm going to tell us that our system is operating at a frequency of 50 hertz, because without that, we literally cannot get it. So what I'm going to do here, I'm going to put a line, and then I'm going to write down our equation for capacitance.
US power function 60 hertz.
60, yeah. So we are correcting something in Europe. Or yes, I don't remember if it's the southern or northern half of Japan, but yes, one half of Japan. So the capacitance C is equal to P old times the tangent of theta old minus the tangent of theta new divided by omega times the magnitude of the voltage drop across the capacitor squared. Which of these pieces of information do we presently have? So we have theta old for sure, because it's literally this. We don't have P old yet, but we definitely have enough information to know P old, right? So I'm going to say that theta old is equal to 24.434 degrees. We got that, okay? How do we find P old? this quantity right here, S total, represents the total complex power supplied by my source prior to power factor correction. So the real part of this is just P old, right? So we know that S old is equal to 65.578 with the 65.578 is the apparent power, yes. 24.434 degrees kVA, which could be written in rectangular form as 59.704 plus J 27.126 kilovolt amperes. This part right here is P old, the real part. So we have P old, we have theta old, so we are lacking theta nu, omega, and VC, for the magnitude of VC. So how do we get theta nu? Exactly correct. Inverse cosine of PF nu, which is the inverse cosine of 0.95 18.195 degrees. All right. How do we get omega? 2 pi times F, exactly correct. So omega is 2 pi F, or 2 pi times 50 hertz, which is 100 pi radians per second. And now we need to know the magnitude of the voltage drop over our capacitor. So I'm going to scroll up to the top here in just a moment as soon as people stop writing, because I don't want to interrupt them. All right. So hopefully we can all see that the voltage drop applied across the capacitor is the same as this source voltage, right? So that begs the question, how do we determine the source voltage? Well, I would argue that it's just the voltage drop over our transmission line plus the voltage drop over our loads. And since we know our transmission line current, it's pretty easy to determine that voltage, right? So VS which, to be clear, is the same as VC that we're looking for, is simply IL times 0.1 plus J 0.2 ohms plus VL, or $130.546 angle negative 22.241 degrees amps RMS times 0.1 plus J 0.2 ohms plus 480 angle 0 degrees volts RMS which I get to be 502.334 angle 2.193 degrees. And so the magnitude of VC that we need, oh, sorry, and this is in volts RMS, is simply 502.334 volts RMS. So we're out of time here, but we have absolutely determined every different number that goes into this equation. So at this point, it's literally just putting it in the calculator and saying we're correct. All right, so you scroll back down for those of you who are still copying stuff. No. Actually, yes, we could have done that as well. 100%. Yeah, so S total divided by the complex conjugate of the current would have given us VS as well. Yes, I didn't even think about that. I went the KVL route, but there's nothing wrong with that either. I guess realistically, that would have been a shorter calculation because it only would have involved two numbers as opposed to my three. So 100% correct.